We are discussing about fundamental matrix of a stereo geometry, and we have seen how fundamental matrix plays a very distinctive role in characterizing its geometry. And in the last lecture, we discussed how fundamental matrices could be estimated given the observations of corresponding pairs of points, and also some parametric forms of representation of fundamental matrix, which also sometimes helps us in formulating the estimation problem. Now, in this lecture, we will be discussing that how we can retrieve the camera matrices from fundamental matrix F. So, note that in our previous problems, we have not considered estimation of camera matrices. If we know the camera matrices, then computation of fundamental matrix is very direct, it is very simple. We will see here the reverse is not the same. So, let us consider these aspects, that F, that is a fundamental matrix, it only depends on the projective properties of P and P prime. So, given a pair of P and P prime, you get an unique F, and the interesting part is that it is independent of choice of world frame, means world coordinate system. That means, if I have a stereo setup and I can move this setup by keeping its relative orientation the same, relative orientation of the image axis the same, I can move this stereo setup in at any point of the world frame, whatever may be my world coordinate convention there, still I mean I should have of course fixed world coordinate system, and then I can move the stereo system at any point, still will get the same fundamental matrix, which is not true for projection matrix. If my world coordinates also move, and based on that the corresponding points of image coordinate and world coordinate points, that will change, because world coordinates have been transformed, then your projection matrix will also get transformed. But this is not true for fundamental matrix, it is solely dependent on the image coordinates. So, if you have same pairs of image coordinates for the corresponding pairs of points, you will get the same fundamental matrix. As you know that even if you move the cameras at any point in the imaging system, the coordinates will vary, but still fundamental matrix will remain the same. So, this is one of the interesting property. So, P prime gives a fundamental matrix F, it is unique. So, the question is that whether we can get the projection matrices P and P prime from a fundamental matrix F. Now, this is a property which we can, or this is a particular fact which we can easily verify, and by which we can see that we do not have an unique solution in this case. That means, though projection matrices, a pair of projection matrices P and P prime gives an unique F, but there could be other pairs of projection matrices which can give me the same fundamental matrix F. So, you consider this situation that there is a homography matrix in the form of 4 cross 4 homography, which means it is a linear transformation. So, if I multiply P with a 4 cross 4 non-singular matrix, which is invertible matrix, so I can from PH I can again get P, there is no problem, I can simply multiply with its inverse. But the thing is that if I multiply PH H with this P and P prime with H, then I will get the same F, that is a theory. So, the proof is that, so in the, if I consider a particular scene point x and consider this stereo system, then the corresponding pair of points will be p x and p prime x. Now, consider a transformation of scene point by this homography, 4 cross 4 homography. That means, by a 4 cross 4 non-singular matrix, a linear transformation. So, you know that X is a 4 cross 1 column vector. So, if I multiply with 4 cross 4, it still remains a 4 cross 1 column vector. So, now you consider, rather I will make H inverse instead of H, let me do it H inverse. H inverse will be also a 4 cross 4 matrix, because I mentioned H is an invertible matrix. So, if I consider another projection matrix P H and multiply with H inverse x, you will get P x, the same points. Similarly, P prime H multiply with H inverse x, you will get P prime x, which are the same corresponding pairs of points. So, same corresponding pairs of points have these solutions. It could give me a fundamental matrix satisfying a set of projection matrices in the form of P H, P prime H and corresponding scene points as H inverse x. So, this is what is this proof, and that is I can summarize once again just to make it a clean display. So, this is just we derived, this is the scenario. So, the summary is that F does not uniquely map to P B prime. So, once again we continue this discussion. So, let us consider this particular scenario we discussed earlier, that projection matrix is in the form of a canonical form, that is for the reference camera, which is given by this I 0, whereas the other projection matrix, other camera, it is not given in canonical form, but it is represented into this form M M. Then we know that given these pairs of projection matrices, its fundamental matrix of the stereo system can be computed using this expression. Note that this M is the right epipolar. That means, this column vector is the right epipolar of this. So, and this M provides you also the homography at infinity. So, we note E prime cross homography at infinity, that gives you a fundamental matrix, that is the relationship we have discussed here. So, this we discussed that if we can derive F, if we get F from two camera systems, the same F, then there should be a relationships between the projection matrices of these two camera systems. It corroborates with the theory what we discussed in the previous slide. And we can explain that because of this constraint, we can explain how degree of freedom of F is related to the degree of freedom of projection matrices. Say, we know that number of independent parameters of a projection matrix is 11, just the scale, that it should be scale equivalent, that is all. So, there are 12 elements, and so number of unknowns are 11, or number of independent parameters is 11. So, since there are in a stereo system, it involves two projection matrices. So, maximum degree of freedom could be 22, but since they are related by this homography, 4 cross 4 homography, once again 4 cross 4 homography matrix is also a projective element. That means, there is it is described up to scale. So, one of the element could be a scale element. So, there are 15 degree of freedom of H is 15. So, that is the constraint imposed on a fundamental matrix, that given that fundamental matrix projection matrices should be related given any reference projection matrix. So, 22 minus 15 will give you the degree of freedom of F. So, this just justify how also this is also corroborating the fact that degree of freedom of a fundamental matrix is 7. There is another interesting fact that we would like to discuss, that the fundamental matrix corresponds to a projection matrix P and P prime if and only if P prime transpose F A P is a skew symmetric matrix. That means, it checks the compatibility. So, if I give you a fundamental matrix and if I give you P and P prime, immediately I can check with these relationships whether they are compatible or not. I need not compute F from P and P prime to check it. I have to check the scale equivalence there, of course, but in this case simply I have to check whether P prime transpose F P is skew symmetric. So, what is skew symmetric? Just to remind you, a skew symmetric is a matrix where the transpose of this matrix should be the negative of this one and the diagonal element would be 0. So, this is one example. So, if this element is A, in this case it will be minus A, and off diagonal elements are related in this form. So, if I take the transpose, you get the negative of this matrix. So, that is how the skew symmetric matrix is defined. So, just to prove this fact, one of the interesting property of skew symmetric matrix that is exploit, that if you consider any skew symmetric matrix, then this fact is true. That means, x transpose S x equals 0 for all x. You have to choose the proper matrix dimension. So, a skew symmetric matrix has to be a square matrix, and when it is true for all x. So, if it is a skew symmetric matrix, it has to be true for all x because of that negation properties, that transpose of this is a negation. So, now we will be showing that if I perform this operation x transpose P prime transpose F P, this is the matrix which is considered this matrix S. If I perform this operation by applying the relationship of fundamental matrix, this is true for any x in the P cube. You see that this is true for only the corresponding pair of points, but for any scene point in the 3-dimensional space or in the homogeneous coordinate 4-dimensional homogeneous coordinate space, this is true. And that is how if this quantity P prime transpose F P, this is a skew symmetric matrix. Then another relationship we need to we will be noting here, that F corresponds to P and P prime, where P prime is given in this form. That means, one of them is a skew symmetric matrix, S is a skew symmetric matrix, and F is the fundamental matrix. So, this relation is giving me a particular pair of projection matrices. It is helping us to form at least a pair of matrices where which will give me the corresponding F. So, I will not give the details of the proofs, but these results are interesting. So, that we will be getting here. So, one of the good choice of a skew symmetric matrix we have already discussed, that is E prime cross. We know E prime cross is a skew symmetric matrix, and if you remember that if I consider E prime, if I represent E prime as say E x prime, E y prime, E z prime, then E prime cross is given by a skew symmetric matrix in this way. So, this is E z prime, this is minus E z prime minus E x prime, and this is E y prime. Similarly, this is E z prime, this is minus E y prime, and this is E x prime. So, you see that this is a skew symmetric matrix. So, the solution from F, at least we can get one pairs of projection matrices. One of them is in the canonical form I 0, and the other one would be E prime cross F E prime. So, this is at least a solution you can get from here. So, this is what I just mentioned, that given a fundamental matrix, at least you can get a pair of projection matrices in this form. But as we mentioned, there should be a family of projection matrices, pairs of projection matrices, which will give you the same fundamental matrix. Now, this family is shown here also. Once again, the results, no, we will discuss the results, but not the derivation. So, here you can see that this is the these are the equivalent pairs of projection matrices, which will give you the same fundamental matrices, or this is a family of fundamental matrices. So, what is the definition here? See, V is any 3 vector and K is a scalar constant. So, the K E prime is the same epipoles that you expect there, and E prime V transpose, it is a 3 cross 3 matrix. Once again you can multiply with it. For essential matrix, we can also derive the camera matrices. As you can see that essential matrix is given in this form. So, once again this is a T cross is a skew symmetric matrix, and R is a rotation matrix, which is an orthonormal matrix. So, this is a kind of decomposition. So, given an essential matrix, if I get a decomposition of skew symmetric matrix and rotation matrix, which is an orthonormal matrix, then I should be able to get at least a pairs of projection matrices given P equal to I 0 and P prime is R and T. And the other fact we have already mentioned, that 2 of its singular values are equal and the third one is 0. So, the matrix decomposition of E should give me the corresponding pairs of matrices. Now, there is a technique which ensures this decomposition. So, we have to perform singular value decomposition of essential matrix in this form, what is given here as you can see, and there are 2 possible decomposition of essential matrix in the form of a skew symmetric matrix and rotational matrix, where you can see that it is a this E equal to S R, and S is given in this form U Z U T U transpose. So, U comes from the definition of the singular value decompositions, and R is U W V transpose or U W T V transpose, and you can find out the form of Z and W. So, this is one particular solutions. You need to perform the singular value decompositions, and then Z and W, they are well defined, and you can get the corresponding matrices. So, some more elaborations, that any skew symmetric matrix S can be decomposed into this form, you can show, and even if you can multiply with a scale k, as I mentioned, that always for any fundamental matrix or essential matrix you can multiply with a scale, and you can show that W is an orthogonal in the orthogonal form, and Z is diagonal 1 1 0 W. So, there is a relationship between Z and W. We will see the motivation of why we are explaining these properties. So, by exploiting those properties, these are the possible configurations of the projection matrix of the second camera. So, first camera's projection matrix is already taken as I0 in the canonical form. So, these are the possible configurations. As you can see, there are 4 such options are there. You note the definition of U3 here, which is the last column of the matrix U, which is given by this singular value decomposition, which means U3 corresponds to the singular value 0 of U. And but out of these 4, only one is valid for viewing a point from both the cameras. We have already discussed that given a camera matrix, how you can decide which point is in front of the camera. So, one of these projection matrices will have the same frontal directions, same directions with I0, and you should consider that that matrix which satisfies. So, this is one form of solution of projection matrices from essential matrix. So, let us consider an example here using those properties. Now, this problem says that you have been given a fundamental matrix and also the projection matrices P and P prime of the stereo vision system. Now, you have to check whether they are compatible or not. We discussed this particular property. We have to exploit the property that P transpose or P prime transpose F P, it should be skew symmetric. So, we need to compute this particular element, particular entity, and if I perform matrix multiplications, I will get this matrix, and you can observe that this is not a skew symmetric matrix. So, which can readily tells us this fundamental matrix is not compatible with these cameras. So, it is not compatible. We will now consider another computational problem, that given a pairs of corresponding points, a set of pairs of corresponding points, how can you compute the scene points? We sometimes refer the whole ensemble as a structure of an object, because if you know the 3-dimensional coordinates of the object points, we consider we have recovered the structure. So, essentially we would like to compute the scene point, ith scene point, I can say also xi, ith scene point whose corresponding points are given by small xi and xi prime. So, one of the strategy could be that I can easily compute fundamental matrix F. Then I need to find out P and P prime. So, which may not be unique, but at least it gives a plausible structure, and then I may later on do post processing to get proper combination of P and P prime to get a structure. But right now, let us consider only that whatever P and P prime we get, we need to compute the corresponding scene points. Then we can apply the triangulation. So, we will explain what is this method by which you can get the scene points. So, triangulation method, it says that if I have the scene point xi, say you have a image plane corresponding to this camera whose center is here C, and say this is your image point xi. So, I can always form, given its projection matrix P, I can form the back projection ray. So, I can form the equation of the projection ray we have discussed earlier. Similarly, for the other camera, I know its camera center of the camera and its scene point. I can form the other projection ray, which means I would get the equations of straight lines in a 3-dimensional space. So, now ideally they should have intersected to my scene point, but there would be errors due to observation, errors due to computation. So, they may not exactly intersect. So, what I should consider? I should consider the closest point which should have been an intersecting point. So, consider a perpendicular projections from this line to the other line. So, that is a linear segment, and take the middle of that line segment, and we will consider that is my scene point, that is the solution. So, this is what we will compute intersection of C x I and C prime x I prime, and for that we need to compute the segment perpendicular to both and get the midpoint. So, you should note that this computation is not projective invariant, because as we mentioned that your camera coordinate, your camera matrices could have been P h, P prime h. Of course, no, if it is P h, P prime h, you would have got H inverse x. But the thing is that the way you are doing, you would not get H inverse x if you take also P h, P prime h. So, that compatibility is not there. It would be close to that, but it is not, theoretically it will not ensure that you will get H inverse x. Another method could be that we can estimate the scene point by minimizing certain objective function by considering the projection of those scene points applying the projection matrices. So, in this case you can see that what you can do is start with an initial estimate and then observe what is your image point. Now, those image points should be close to your observed image point. Then you this is a image point you obtain from computation, and these are the observed ones. So, if your estimate is good enough, this error should be very small, and they should also satisfy this constraint. So, once again this is a constraint based optimization problem. It is a nonlinear optimization. There are various nonlinear optimization techniques by which you can solve and you can refine your estimates, and this method is particularly projective invariant. That means, if you take P h and P prime h using this method, the solutions will also satisfy H inverse x and H inverse x prime. And the linear triangulation methods we have discussed, I think this is so. In this method, we will be using the algebraic manipulations. In the previous case of triangulation, we considered only geometric method of computing the intersections of two lines, but here we will formulate this problem as a solution of a set of linear equations. So, we will form a set of linear equations. As we did in previous cases also, you will find out similarity, we will find the similarities of these formulations. So, since we have a pair of points x I and x I prime, we can consider that it forms an equation, say let us consider any pair of points, say x and x prime, instead of I will not use the index I here. Since P x is the same, P x gives me the same point, but once again since it is a projective element, it could be scaled version of x, but the direction will remain same as a vector. So, if I take the cross product with x, that should be equal to 0. So, this will give me a set of linear equations for which satisfies this constraint. Similarly, x prime cross p prime x, that should be equal to 0, that would give me another set of equations. So, if I expand this particular form, I can write it in this way, say P could be, let me write P as R 1 transpose, R 2 transpose and R 3 transpose. This is the form of P, and so P x is a vector which is R 1 transpose x, R 2 transpose x and R 3 transpose x. So, you see that this is a 3 vector, and similarly x also a point where we can represent in this form. So, x y 1. So, I have to take the cross product of these vectors. So, I will form this equation x y 1, then R 1 transpose x, R 2 transpose x and R 3 transpose x. This is the cross product, and there, as you can, if I expand this cross product once again, so you will find that y R 3 transpose x minus R 2 transpose x, this should be my x component. The y component would be R 1 transpose x minus x R 3 transpose x, and z component would be x R 2 transpose x minus y R 1 transpose x. So, this should be equated with a 0 vector, because that is the meaning of this cross product. So, this equation should be equal to 0. So, we will get this set of 3 equation y R 3 transpose x minus R 2 transpose x, that is equal to 0, R 1 transpose x minus x into R 3 transpose x equal to 0, and x into R 2 transpose x minus y into R 1 transpose x equal to 0. So, you will find actually the third equations can be derived as a linear combination of these two. So, you multiply with x and multiply with y, and then if you add them, you will get the third equation. So, which means there are only 2 independent equations. So, it will give you only 2 equations. Similarly, this point, this constraint will give you another 2 equations. So, given a pair of corresponding point, you have 4 equations, and how many unknowns you have for x? You have only 3 unknowns, because these are the world coordinate points x, y, z, and there is the scale dimension. So, there are 4 equations and 3 unknowns. So, once again you can apply the least square error estimate technique that we did. So, just to summarize this particular computation, we can consider that there would be 4 equations, 3 unknowns as we mentioned, and this can be expressed in this form, set of linear equations. So, once again the same, it is a set of homogeneous equations. So, we have to minimize the norm A x subject to norm x should be equal to 1, that is the constraint we will impose, and you can apply the direct linear transform that we discussed earlier also for estimation of projective transformation matrix or homography matrix, and this is not a projective invariant. We can generalize this particular construct, that is the power of this technique, because if you have 3 point correspondences, that means you have a 3 camera system, say P 1, P 2, P 3. So, each one will give me this similar form of equations. So, each one means each one will give me 2 equations. So, there are 6 unknowns, 6 equations, but there are again 3 unknowns. So, you can solve using the same technique. So, I think with this let me stop here. We will continue this discussion of structure recovery in our next lecture. Thank you very much.